Hi, everyone. Welcome. Thank you for coming to the International Day for Women in Statistics and Data Science. We are session 6, Advancing Healthcare with Data Science and Machine Learning, the Future of Data-Driven Care. Our first speaker is Dr. Sharma, and she is an assistant professor in the Department of Mathematics and Statistics at York University, with cross appointments as an assistant professor at the Dalai Lama School of Public Health, University of Toronto, and a clinical investigator at the University Health Network.
Thank you, Jessica, for that introduction. I would like to share my screen now. I hope you can see my screen.
You can.
Perfect. I'll just put the slideshow mode on. Perfect. So, hi, everyone. My name is Divya Sharma, and today I'll be presenting my talk on harnessing data science and machine learning for personalized osteoarthritis treatment. And it'll be a multimodal deep learning framework that I'll be discussing in my talk. Why is it necessary to look into this particular problem statement? So knee osteoarthritis is the most common form of osteoarthritis over the world. Up to 34% of patients that undergo a particular surgery called as total knee arthroplasty, they do not show improvements in pain and function 1 year post-surgery. So that's very, very challenging. When we look at the psychosocial or socio-demographic variables of those patients, it's very insufficient data to explain the differences in the patient outcomes post-surgery. Therefore, researchers are looking into molecular variables such as RNAs present in the genomic data and metabolites present in the plasma to help them see what guides this pathogenesis of OA and what can inform post-surgery pain and function responses in the patients. So the motivation for this particular research project was to use individual biofluids such as microRNAs present in the genomic samples and metabolites, and use all of this data, which is multimodal, which has various data distributions, and combine them together to provide unique insights that are a combination of all these molecular variables. It's very, very essential for utilizing the complementary nature of these diverse data types. And what we aim to achieve was to use this raw data to cluster patients into groups such that personalized treatment strategies could be given to those specific groups. Now, the major question comes here that how to effectively combine information, which comes from, as I mentioned, many, many data distributions and different modalities with their own sets of pre-processing steps, etc., and harness this information together to inform prediction and analysis. This becomes a critical challenge, and this is where deep learning comes into picture. Deep learning is a very popular subfield of artificial intelligence these days, being used all over in applications in various research areas, and particularly in healthcare. Artificial intelligence is incorporating human intelligence to machines. Machine learning deals with incorporating this intelligence to computers to help them learn like humans do. And deep learning is a much more nuanced branch of machine learning, which deals with emulating how a human brain learns things, how a human brain perceives patterns through neurons in our brain and the activities that neurons conduct when they see a pattern, etc. And that's how deep learning wants to emulate that process in the human brain and transfer it into machines, specifically computers. Why is it called deep learning? Because we have this very layered networks, which are known as neural networks, which have many, many layers, each layer doing a specific task of automatically extracting relevant features at different levels from your input data. For example, if you have a skin lesion, the first layer of a deep learning neural network would identify the most basic form of features from the skin lesion, which would be perhaps edges. The second layer would go one step further and try to understand the associations between the first level features that are the edges. So it will try to identify the boundary that the edges form. The third layer would identify the pigmentation or the coloring. And the fourth layer and subsequent layers will go one level deeper, trying to identify features that are more complex and non-linear in nature. And perhaps in this particular input would identify the difference in colors between in the pigmentation of this particular lesion, and finally predict whether it's a cancerous lesion or not. So what I was trying to tell you here is that each layer has a specific task. Each layer enters a particular level of complexity and nonlinearity in the network, which is very essential when we are trying to do processing from complex high-dimensional inputs. In our project, we looked at a deep learning framework for doing clustering from multimodal data, as I mentioned. So we had a very high dimensional data set with very less number of patients. We had about 414 patients. However, as I mentioned, our feature set was very, very rich. We had about 2,727 features across the multi-domains of data that we had. And because we have less samples and more features, we had to do some sort of dimensionality reduction to address this. And for this particular challenge, we used an autoencoder neural network, which is particularly useful for reducing dimensionality of high dimensional data sets and doing unsupervised learning on data sets to do further clustering. So for a very this is an illustration for how an autoencoder works and what it does. For example, you have a very high dimensional input image of Mona Lisa here. An autoencoder has an encoder and a decoder module. An encoder module would now reduce the dimension of this high dimensional input into simplified features, which would be less in dimension. This is known as a latent representation. Now forget about the input. Basis this latent representation, the decoder would try to decode the input back. So in the first iteration, your decoded input might not look as good as your original input, and you would want to refine it. So that is where you give the feedback to your network to improve it, to improve its learning such that the latent representation is representative enough of your input, and your low dimensional space has accurate representation of your high dimensional space, which can further be used for downstream analysis. So at output iteration 400, you'll see a much better reconstruction of your input. And that's what the autoencoder tries to achieve in a very naive way. And finally, you would use this reduced latent representation for your clustering because your clustering was initially not possible on your high dimensional data set. Variational autoencoders are a type of autoencoders which capture the mean and variance of data, much more nuanced in the sense that they capture the uncertainty in the data better than a basic encoder. So we used variational autoencoders for our methodology. As I mentioned, we had 4 data domains, multimodal data that we wanted to cluster our patients by. We used this encoder, we concatenated or stacked all our multimodes of data together and had individual decoders to decode our input data back such that the latent distribution is now a combination of our multimodes of data and represents our high dimension multimodes of data in an efficient manner. As you see in the central block, we then use this latent distribution to help cluster our patient samples. When we looked at k-means methodology for clustering using our latent representation, we identified 3 clusters, really balanced clusters, which were not possible when we were using individual data domains for clustering, because that was leading us to 10 or 20 clusters and was not informing our downstream analysis well. So this integrative approach really helped us to group patients into 3 meaningful clinically relevant clusters, which we further use for prediction tasks. So the second objective was to, in these individual clusters that we've identified, look at how these patients are responding to knee surgery post 1 year of their surgery. So then again, we had multimodal inputs in the 3 clusters. Individually now, in these 3 clusters, we had machine learning models that were working on these individual data domains together. So now in this slide, I'm showing you another framework of how you can integrate multi-modes of data together for predictive analysis. First, we talked about autoencoders. Now, through this machine learning framework, we had these individual input domains. Unimodal, single mode of machine learning models were used to identify features from these data domains. Further, in the second step, integration of the features identified from these individual domains was done at the second step, not at the first step. So at the first step, we kept these domains intact individually so that features can be represented properly by individual unimodal machine learning models. And then we did the integration of these features. And we then used this integrated feature set for our prediction analysis. And I will show you how that helped, because when we were using these individual data domains, for example, area under the curve is a popular evaluation metric for kind of evaluating any classification or prediction performance of machine learning models. So for miRNA in the plasma, which was one of the domains, the AUC was 0.656. Higher the AUC, better the classification or prediction is. For another domain, the AUC was around 0.66. And for each of these domains, the AUC was around 0.78, 0.72, 0.71, etc. However, when we integrated all of these domains, and I show you here in bold red, the integrated AUC was 0.879, which was much better than the individual domains. And that is what we aim to achieve, that the individual domains perhaps were not informing the prediction as much as the combination of these domains would. And we identified this trend across all the three clusters, and thus could infer that combining the power of the molecular domains that we had and the clinical data as well really helped us to improve the prediction of post-surgery response in patients within each cluster. Specifically, cluster 3 really performed very well in informing this prediction. To summarize my talk, I would like to mention that we discussed two methodologies. One was unsupervised, which was a clustering approach using autoencoders that really helped us capture patient heterogeneity better, helped us identify clusters which were much more dissimilar to each other and had distinct properties in terms of their molecular features. Further, in our second objective, we did a prediction framework using multimodal data. Again, that machine learning framework really helped us identify the power of combining various data domains together for analysis and prediction. And thus, finally, the richness of multimodal data can really uncover novel biomarkers and pathways in various disease outcomes and can help us understand complex diseases better. So one should really look, because we have this rich data all over, so one should really look to harness this integrative power for their analysis and prediction tasks. I would like to thank my collaborators at the Schroeder Arthritis Institute at the University Health Network Toronto that really helped make this research project come to fruition. And if you're interested into the details of our project, I would like you to please go to our Med archived paper. I've posted the PR code here, and you can also email me with your questions on my email ID on the screen. Thank you so much for listening to me. I'll be happy to take on any questions. Any questions? If not, I'd like to thank the audience again. I'll just check the chat if any more questions have been posted there. Otherwise, Jessica, maybe we can go forward to the next speaker if there are no more questions.
Thank y'all for being here.
Thank you. So maybe I can invite Somita.
Somebody wants to know, was the model validated externally?
The model was not validated externally. However, we conducted 10-fold internal cross-validation. This particular data set was very difficult to compile. So I think over the world, there are very few data sets that have this rich information of multi-domains. So we weren't able to get another data set for external validation, but definitely that's our future scope and future goal, to have another such data set. But we did internal cross-validation and the results were comparable to our main test results as well. Thank you for that question.
Do you see the Q&A?
Yes, I do see them now.
There's another one.
Yeah. What do you recommend to keep as considerations in expanding it to other diseases area or care area? I think the considerations have to be that the sample size for any machine learning research has to be reasonable. It can't be really, really small. And if you have a very huge feature set, you would have to do some kind of dimensionality reduction to handle that high dimensional feature set. Now, dimensionality reduction can be done through, say, principal component analysis, but basis your problem statement, you then have to decide whether you want to go for linear combination of your features or whether your data set is complex enough to show nonlinear properties. And if that's the case, then you should look forward to deep learning methodologies or advanced machine learning methodologies. If your data set is simple, you should then use basic statistical PCA-based methodologies for any data dimensionality reduction. So I would mention that as something to consider. Okay, so I think I've answered both the questions. Any more questions? Okay. If not, thank you so much, everyone, for listening. I would now like to invite the next speaker, Somita. Somita earned her doctoral degree in biostatistics from the Soswi Hawk School of Public Health, National University of Singapore. She is now working as a Schmidt AI in Science postdoctoral fellow at the University Health Network lab, which is supervised by Dr. Mamatha Bhatt. They delve into liver disease research and ML methodologies for integrating omics and clinical data for improving outcomes in liver diseases. I would like to welcome Somita for presenting her talk now.
Hi, thank you. Thank you, Divya. That was a wonderful presentation. I'd like to share my screen. Are you able to see my presentation?
Yeah.
Okay. Hello, everyone. So today I'm going to present on the topic advancing personalized diagnosis, prognosis, and treatment of liver diseases through machine learning and data science applied to omics and clinical data. So we have recently published a comprehensive review paper in the journal Gut, and today I would like to briefly discuss some relevant topics from that review. So as you know, study of omics is a very vibrant field, and over the course, we are seeing a slow but gradual shift from traditional data science or statistical methods to more emergent artificial intelligence or machine learning methods. Yeah. So before I go deeper into the review, I would like to let you know a bit about the organ of interest here, which is the liver. So liver is the largest internal organ in the body, and it plays an essential role in metabolism. Chronic liver diseases can take months or years to develop. Sometimes chronic liver diseases approximately takes around 25 or 30 years to manifest. and they manifest quite at an advanced stage. So approximately 1 in 3 or 4 persons globally may be affected by liver disease in their lifetime. And among chronic liver diseases, metabolic dysfunction associated steatotic liver disease is the most common liver disease, affecting more than a quarter of the global population. So currently, the current form of diagnosis and monitoring of any liver disease is through liver biopsy and histological examination or similar means. But the method, liver biopsy method, is very invasive. It's prone to sampling errors, and it's also expensive. It's something that you cannot recommend for a patient to do like periodically because there are risks involved. So there is a significant need for specific non-invasive biomarkers. Now, recent years, we have witnessed the beginning of a new era in biomarker development, and that's thanks to high-throughput omics technologies combined with increased computational power and the ability to use AI and machine learning methods with routine hardware and software. So this major development or this major advancement has allowed us for hypothesis-free testing of thousands or even millions of analytes. Now, omics data is diverse, and each omics data type reveals an aspect of cell complexity. So in general, you would know that there are like 4 main types of molecular components, like the DNA, RNA, proteins, metabolites. Apart from that, there are many others like microRNAs, etc. The scientific field, each of these scientific fields that study each of the cellular component or data level are referred to as genomics, which studies the DNA, transcriptomics, which studies the transcripts or the RNAs, proteomics and metabolomics, and so on. So the common point in all these omics types arise from the fact that they are all from high throughput experiments, which allow simultaneous observation of many individual components. So you can see typically a processed omics dataset looks like this. So you would have features and you would have samples in each of the matrix files. So the features may depend on the data level or basically the omics type. For example, genomics data, the feature type would be chromosomal location, whereas for proteomics, it would be proteins, and for metabolomics, it might be metabolites. So feature changes, whereas the sample could be kept the same, like each sample could be profiled across various data levels. So why multi-omics profiling is so, like, why is it so like up and coming, and why is it recommended now for precision health? Like through the advent of high throughput technologies, like omics profiling has become a more routinely available, or because we are able to basically look at the molecular level of the data, and it's being nowadays carried on at like in laboratories. So earlier it was not cost effective enough. As we are moving towards more personalized healthcare, omics profiling of patients are becoming more and more important. Other factors for omics profiling are for early disease detection. Intervention costs are rather high. When you treat a disease at a very late stage, then the cost or the healthcare burden is high. So early detection is key. Also, other factors for omics profiling are for early disease, other than disease detection, is there are differences in genetics, environment, or lifestyle factors that cannot be captured by only, say, clinical or demographic variables. So there are certain factors that kind of make personalized treatment effective, and that is made possible through omics profiling. Also integrating omics with clinical attributes, which are routinely available in to doctors or clinicians, can help improve diagnostic accuracy. So depending on the problem or challenge at hand, so we can use multi-omics data for a variety of questions, like we would be able to use omics data sets to answer different types of problems in healthcare. For example, you could use omics data for disease risk prediction, disease subtyping, biomarker discovery, molecular insights, or treatment response. So here I kind of use a typical illustration to show how multi-omics data analysis or integration is done. So in biology, since computational models are used to understand complex biological systems, model interpretability and generalizability are key factors for making informed decision in clinical contexts. So most of the studies interrogate a subset of omics data. The data analysis is typically split into steps like a feature selection step and then an AI modeling or machine learning modeling step. The objective of feature selection is there are lots of features with very few samples. Always the number of features are higher than the number of samples. So we need to reduce the dimensionality of the data by identifying key features that are relevant to the problem. In this step, sometimes prior biological knowledge is commonly integrated to improve feature selection. In the AI modeling step, the model learns to integrate the multimodal features selected through the statistical feature selection step and map them to outcomes. So the choice of modeling algorithm hinges on the type of outcome, like is it a prognostic outcome that you're looking at, or a diagnostic or a therapeutic application? And depending on that, you decide whether you would want to do a supervised learning or like unsupervised learning. So the distinctions are not quite always clearly defined, and many studies often use a combination of algorithms to address their question. So here are some of the here is a typical summary of the studies that we have included in this review. For more details, you can look into the paper. But here, to summarize, the study includes those liver-related studies, and which were considered based on the omics diversity, the types of omics that were used, or the algorithmic novelty that they used, or if they had novel biological discoveries. And another factor that was important was cohort sizes. So as you can see, most of the studies still like random forest, gradient boosting, and linear models such as logistic regression with penalty terms are quite popular. And only a few studies have attempted to use deep learning methods. So for example, here, only one study which compares MASH with pre-cirrhotic fibrosis with cirrhotic fibrosis uses a deep learning method. When we continue the table, we see that, however, there is a quicker adoption in HCC, which is hepatocellular carcinoma, because of the one of the reasons is because this field has a lot of more publicly available data sets. So, and the data sets are usually larger in sizes, which makes it possible to utilize them for deep learning algorithms. So another So as I've mentioned before, there's a significant need for non-invasive tests in diagnosing and staging liver disease, especially emphasizing since AI models or data-driven AI models have now become more ubiquitous for omics data analysis. The AI model itself can act as a biomarker in certain circumstances. So what we try to depict here is, in the right, this is the clinical gold standard of diagnosis, which is a liver biopsy. But with sufficient data, this current AI models have the capacity to evaluate many features and learn complex functions and accurately predict outcomes, as well as detect severity. So they themselves can act as a biomarker. So Yeah, that's like if, but the key point here is have to have sufficient data. So, and this would really improve with early detection and disease monitoring. So here, what I tried to show here is the omics modalities across liver diseases. So as you can see, the different types of omics and the different diseases that it was profiled on. And you can see here that the transcriptome is the most widely studied modality, as well as like followed by lipidomics and metabolomics. And as you can see, MASL, which is mostly a disease, a fatty liver disease. So there are more profiles that have more omics type, such as the metabolome, lipidome that has been profiled or studied. So here, we kind of look at all the publications, not all, like the selected publications from 2016 onwards till 2024, and we see that there is a slow shift towards more emergent methods like AI or ML methods. The group, tree-based methods are highly popular in dissecting liver diseases, basically. Here, each dot represents the impact score. So the impact score has been calculated based on the validation cohort size and the AUROC, or the accuracy of the ML model. And you can see the latest trend is moving towards deep learning methods. However, like random forest is one of the most popular techniques with like good amount of cohort sizes. So it has been validated for different types of diseases. And DL techniques have gained popularity, particularly DL techniques when used with histopathology images along with omics modalities have actually gained popularity. Yeah. So basically, I would like to summarize what the review so far. So what we see is like AI methods are for extracting insights from complex omics diseases are still emerging in case of liver diseases, and there is particularly a significant opportunity for novel developments. What we urgently need are large, well-curated, diverse public data sets. And such data sets need to generalize across populations. The other key message that we want to send out is like open sourcing data and code along with standardized reporting of model performance is necessary for AI model reproducibility and reliability. So, and as we see, integrating omics data with other modes, such as clinical radiology or histopathology information, can significantly enhance the prediction accuracy and clinical relevance of AI models. And the key factor in any complex biological system modeling is explainability. If we are able to perform each and every step without losing explainability, I think that would be the ideal key to faster adoption of AI in early diagnosis and personalized treatment, especially for complex models. So with that, I would like to thank you all. And if you're interested, you can go ahead and read in detail this paper, which is available here. Thank you.
Thank you, Samita. Any questions? Maybe I can start with a question, Samita. So that was a great presentation, firstly, very, very clear. I wanted to ask, in one of the slides, you mentioned a step which was feature extraction and then using an ML methodology. So I just wanted to know your thoughts behind when we talk about deep learning, it says that one should not look for any prior knowledge to be incorporated into the network, because deep learning does its own feature extraction, etc. So you should not bias it in that way. So what would you recommend in that scenario where one wants to use a deep learning model rather than a basic machine learning model in that scenario?
Yeah, I think yes, I think deep learning models, the main thing is like we could probably look at probably model interpretability. For example, we could later check through SHAP or basically some model agnostic explainability techniques to see if the model is actually learning biologically relevant biologically relevant or the system. The reason why we try to infuse prior biological knowledge is so that whatever we have learned so far about the whole biological system is not lost. But if we see that the deep learning method is able to capture those interpretations correctly, I think there is a reason, there is no need to do feature selection in that case, and can directly use a deep learning method end to end. I would say.
Yeah, I think that is great. Thank you for that answer. We have two questions from the chat. Surbi is asking, how do you mitigate biases in ML models trained with omics in cases where certain populations may be underrepresented? A very topical question.
Yeah, I think the key here is not to overfit models. So basically, if we are able to learn certain features that are the key here is to not learn complex features or say that is very specific for certain like populations, or rather learn certain patterns, which is I mean, if, when you use a machine learning algorithm, there could be ways to check if you're like through SHAP analysis or through some sort of explainability, that if your model is capturing certain biases, or is it capturing certain specific characteristics of certain race or subpopulations, and those are certain things you would say that then the model is not performing accordingly. And the I think the ideal case would be to kind of train on more and more data. As you train on more and more data, you kind of reach to a point where it's more generalizable to the population. So sort of like the goal here is to not learn subpopulation specific characteristics, or to learn certain features like overfit the model just to achieve certain level of accuracy. I would say that is how a way to mitigate biases will always be there, but certain biases are completely you cannot ignore them. You cannot So that has a certain sort of mitigation has to be in place.
Yeah, sure. I think we have a minute left to Ghazal's presentation. One more question, if you can answer that in brief.
Okay.
Giali is asking that, are there clinicians involved while developing these models and reviewing these models? And additionally, were there any demographic characteristics used as features as well?
So yes, of course, there is involvement of clinicians here, because they kind of the goal truth, or basically the biopsy they kind of give you the actual biopsy report, or they kind of actually classify whether it's a true classification or not. So that is determined by a clinician or a pathologist. And the other cases, like, yes, demographic characteristics are included. Like a lot of models nowadays integrate both omics profile as well as their demographic characteristics, because a lot of omics profiles such as is dependent on factors such as age, sex. So yes, demographic profiles are included. I think more often you will see now that's included.
Perfect. Thank you, Samita. I think let's move on to Ghazal's presentation. Thank you for your talk. I would like to introduce Ghazal now. Ghazal has earned her PhD from the University of Wisconsin. She specializes in analytical chemistry and bioanalysis in her PhD. Right now, she's working as a member of Dr. Mamata Bhatt's lab at the University Health Network with the Transplant AI Initiative. And she integrates clinical expertise, computer science, and data analytics to advance transplant medicine and understand post-transplant complications. We welcome you, Ghazal, to present your talk. Looking forward to it.
Thank you, Deep. Hello, everyone. We heard we heard about like omics data and multimodal AI, but how we can actually use this multimodal AI in clinical practice and what are the challenges ahead of us. Here is an overview of the talk. I'm going to start with the clinical vignette, explaining the complexities in day-to-day practice. Then I will talk about multimodal AI, its impact, and provide practical consideration for deployment, touching base on the challenges ahead of us. Consider a 57-year-old male who presents to emergency department with confusion. His medical history includes a liver transplant, 6-year LDL for alcohol-related liver disease. Here you could see their laboratory investigation as well as diagnostic and examinations. The clinician cannot actually diagnose this patient until they perform a site fluid culture as well as blood culture to finally understand that this patient has developed sepsis, which is a kind of an infection. This case is very difficult to diagnose because it has similar symptoms with many transplant-related complications. There are currently sepsis detection AI models that have been deployed in clinics, but they haven't had, or they have had a limited improvement in clinical judgment because they are solely using one tabular data extracted from clinical reports, and they lack inherent lack information inherent to the complex relationship between the different data modalities that are usually time sensitive. If we could actually deploy AI models that actually can harness this statistical and mathematical information into multiple data modalities, then we might be able to transform healthcare and move toward personalized medicine. But what is really multimodal AI? We know we have like different data modalities, and while a multimodal AI model is not necessarily a foundation model, which is trained on a vast data set to be adaptable to different tasks, foundation models are increasingly incorporating multimodal capabilities. While each modality is being added to the model, it provides a unique insight into the patient pathophysiological status. And by adding more information, we expect to have better performance for the AI models. Why going toward the multimodal AI? Because we can automate mundane tasks using multimodal AI. We may have better predictive performance via single modality because we can ascertain complex nonlinear relationship between the modalities, and we can compensate for missingness by using complementary modalities. We can use multimodal AI in prevention, for example, for screening healthy population and find out those individuals who may benefit from a screening at younger age, or identify those patients who may benefit most from vaccination, or improve life expectancy of the elderly by predicting their falls much before it happens, much sooner than it happens. We can also use multimodal AI in diagnostics, for example, in cardiology, when there are multiple data modalities used, for example, ECG, echo, CT, MRI, and each of them provide distinct information to the physician. Or it can be used in a situation where obtaining a modality may negatively affect patients' health, like in pediatrics, that frequent radiology for pediatric patients with asthma can have a profound effect on their health, or in situation where there is a limited communication between the physician and the patient, like neonatal care, that mostly the decisions are made based on maternal information and cry recording. You could see how complicated this could be. And then it could also be used for treatments and selecting individualized treatments. For example, in glioblastoma survival, but without any treatment, they survive only 3 months, but with treatment and chemotherapy, they can live for 12 months. But there are some people that can survive much longer, and that's because of their genetics, pharmacogenetics, and demography of the patients. If we could find out and take multiple modalities to reveal patterns that accurately predict which treatment are associated with the best response outcome on an individual level, then multimodal models can be the backbone of successful personalized medicine. We can also use cross-modality, meaning that a model that has been trained on CT scan can be used for ultrasound, or vice versa, or we can have cross-organ transfer learning, that models that have been trained on mammograph can be fine-tuned for brain or prostate cancer diagnosis. That's really interesting. At the heart of multimodal AI, as Divya was mentioning in her presentation, it's a fusion of different modalities. This fusion can happen like at earlier stages when the modalities are encoded before inserting into the model, or they can be encoded while the model is being trained, so that the models are there's an optimization for the encoding of the models as well, and it can also happen as a late fusion, meaning that we train single modalities, and then due to some method like averaging, find out the final decision. It is said that joint fusion methods might be the go-to method in future, but it depends on the task for sure. And what are the practical considerations? First of all, development of a multimodal AI starts by optimizing single modality models as baseline, which then serve as an input for fusion models. Various fusion techniques are compared to identify the best approach for a specific task. And then single modality models can be retrained for later use in real-time deployment of the main model to provide incremental prediction for the patients. This is particularly helpful in healthcare that data are commonly accessed at different time intervals. For example, 100 data points per second from a monitor, or lab result every 12 hours, and vital signs every 4 hours. And once all the data is available, the single mode modeling is completed, we can actually perform multimodal AI. And what are the challenges ahead? The first is the nature of the multimodal data. For example, it's very large, it's heterogeneous data set. There is like intermodality relationship, and as was the case with like the Divya's as well as like Somita's presentation, there is not much of international dataset benchmark for testing this testing and creating best algorithms for tasks. Different modalities might have different labels across different different departments, and different modalities may have different importance across different patients. The level of the missingness might be different, and it might be really difficult to align modalities that are or data modalities that are actually coming at different time points. How we can select an appropriate model, it really depends on the task, but usually if the data structure is unknown, it's an ad hoc process, and we need to try different models until you understand which is the best model. But if the relationship and the data structure and the relationship between the data modalities are known, then we can use known models. For example, if there is like a time dependence in the data set, we can use the family of RNN, LSTM, or transformer. If there, like many biological diseases, like disease, if there is like hierarchical organizations, we can use graph-based method. And if we are trying to deploy it in a dynamic environment, we need to consider like reinforcement learning, that so that the model is adaptable to different changes. For validating this multimodal AI can be in supervised learning can be really similar to the single modality, but we need to consider that different modalities may provide discordant information, and in this situation we may need new validation methods. For example, we could use weighted metrics to actually use for certain modalities or specific time points. It might be the situation that the model just uses, for example, this was based on a study that the model was basically using only like images and like was ignoring all the clinical information, but they incorporated the dropout method so that the model used clinical information as well, and they showed that the accuracy of the model increased. Another problem is the generalization. Even within one hospital, there are temporal concerns, dynamic changes, things that we cannot predict, like happening, like pandemics that happen. By adding each and every modality, we actually increase the risk of data and model drift. And if we come and use like a specific architecture, we might introduce compositional biases, especially in diagnosing the diseases with similarity across modalities. And it's very important that we can actually overcome like the generalization problem. All of these methods or these tools that are being created at the end must be perceived useful and be easily and can be easily used by clinical staff, because if the technology cannot does not increase the task efficacy and minimize the error, it cannot actually be used at the end. There are always concerns about the fairness of the multimodal AI, which integrate heterogeneous data from various sources, adding complexity in ensuring fairness to challenges in managing relationship and balances among diverse data modalities that vary in a scale and time point. The predictive nature of the AI models means that decisions are made based on partial information and similarities to other cases, making it difficult to create an entirely unbiased model. The key challenge is understanding and mitigating the consequences of different forms of bias within the context. Addressing it should involve a stakeholder-driven approach where quality measures for AI system are co-designed by clinicians, engineers, patients, regulatory office, and anyone who is really involved. For example, when we are training AI to achieve demographic parity, such as equal positive prediction for male and female gender may be suitable in the context like loan recommendation, but could be inappropriate for medical AI tools for breast cancer diagnosis. Similarly, allowing some underqualified candidates for a job interview might be acceptable, but in clinical diagnosis, while false positive can lead to harmful or costly treatment misallocations. The key and the future, and you can see that the future, a key to the future with the multimodal is like personalized medicine, that by integrating different type of data, omics, pharmacogenetics, clinical radiology, CT scans, imaging, all of these, we can actually move toward personalized medicine, and we can using like that, and we can and one very useful use is that we can democratize health, and we can provide health to locations that they don't have enough access to physicians. Yes, and we can actually bridge the healthcare gaps in under-reserved and remote regions. For example, using telemedicine platform enhanced with multimodal AI capabilities can facilitate remote consultation and provide real-time diagnostic support, ensuring patients receive timely and accurate medical attention. At the end, I want to thank you, everyone who has helped in putting together this presentation, and I'm happy to answer if there is any question.
Thank you, Ghazal. Any questions? Maybe I can start again. Ghazal, thank you for that presentation. I think you listed out all the challenges and the complexity associated with multimodal data in detail. Thank you for that. I had a question regarding the fusion methodologies you mentioned. I would like you to comment on whether one should explore each of, say, early, late fusion methodologies while they're working out their development of their model, or there is one particular fusion strategy preferred over the others in a particular scenario. Can you?
Basically, it's an ad hoc for a specific. It's an ad hoc process for a specific problem. But I feel like it is, if we do like this joint fusion, that we do the encoding and like addition of all of the data modalities happen at the same time as we are training the model, that would be the best approach. But it really depends, you know, and I feel like your presentation was the same. You were actually doing through this encoder, decoder, we're doing some sort of like a joint fusion, but it was before training the model. But, you know, if we never try it, we don't know how it works with a specific data set, especially like considering the sizes, size of the cohort.
Okay, so then you recommend trying every particular fusion methodology, joint being good, but trying out every
That's
method.
what's recommended most in the literature.
Okay. Thank you.
Thank you.
Any other questions?
Thank you very much.
Thank you, Jessica. Thank you. If there are no more questions, I'd like to thank the audience for listening in, and thank you for hosting this session, Jessica.
No, thank you for submitting it.